All right, welcome back to ArmanisMath. Today we're going to focus on parametric relations and inverses. Parametric relations and inverses. And I want to give you the 50,000 foot level vision of this. And it's basically this concept here. I'm only talking about the parametric right now, not the inverses. The concept of parametric, if I were to sum this up, is let's pretend that you have a toy factory. What do you have here? Somebody tell me in the chat, what do you have? Or in the live stream comments? Exactly, a toy factory. So we got some raw materials coming in. So we're gonna call them some X's. So let's say that you have some threads or some cushion, whatever that's used for toys. And then you got some Y's, the number of toys coming out. Okay, so something going in as raw materials and a number of toys going out. Okay, this is let's say this is Dahlia's factory or something. Dahlia's factory, toys factory. Okay, I wanted also you to think of the X's, the raw materials, taking some time to get to the factories. Let's say it takes about 25 hours to get there. You got some transportation, some scheduling, some other things happening. So the number one thought here is you have X's, raw materials, but they do take time. Okay, they take time, and the time is about 25 hours. Once they arrive at the factory here, this, whatever the machines that you have, chugging along, and all of a sudden you see that you have a certain amount of toys leaving, but they leave after 30 hours of whatever work that has been done on these raw materials. So that's going to be number two. So thought number one, you have basically some raw materials that takes time. Thought number two, you have some toys that also takes time to produce. So let's say that's your top executive, just like Dahlia. Your top executive, you're probably the CEO or somebody who doesn't really concern that much about time. You left the time for lower management to worry about and the scheduling and stuff. You just want to see what is coming in, yeah, and what's leaving. What's coming in and what's leaving. What's the X's and what's the Y's. So your concern now is how to eliminate, get rid of the time frame. There's no time involved here. If you want to take a look at the bigger picture, you don't want to think about time. I just want to know how many things do we have to get in, how many toys are we going to produce. Okay, so in taking out the time from the equation, we call this as eliminating the perimeter. You eliminate this t thing. So you're going to find an equation that has x's and t's, and then you're going to find another equation that has y's and t's in them, and you're asked to eliminate the t's. The concept is very simple. Or what you have to do is solve by substitution. Solve by substitution is basically what we're going to do. Okay? So before we dive into this concept here, I wanted to give you what they wanted us to think of. So they gave us two equations here, and both of them in terms of t. And it doesn't have to be time. I'm just saying that was just one example that I gave. So x is t plus 1. Y is t squared plus 2t's. First of all, they said, you know what? We're going to give you some values for t, like t equals -3, -2, -1, all the way to 3. And why don't you construct a table? Make a table that has some t's column, a t's column, x and y, and then also x, comma y. And luckily enough, they gave us that table here. So they said, for example, if t is -3, so what is x? Well, x is t plus 1. So -3 plus 1 is -2. What is y? Well, y happens to be t squared plus 2t's. So -3 squared plus 2 times -3. How much do you think I'm going to get? What's -3 squared? What is -3 squared? 9. And then you got 2 minus times -3, that's -6. So 9 minus 6 basically, and you're going to get 3. And another last column, they wanted you to put it in terms of x and y. So just what's the x's? -2. What was the y? 3. Okay, let's talk about the 2, for example, here. If the t is 2, then the x is t plus 1, that's 3. And then the y is again, the 2 squared is, what's 2 squared again? 4. And then 2 minus 2 times 2, I should say 2 times 2, which is 4. So 4 plus 4 is 8. And then they just wanted you to set it up as x and y. So what was the x? It was 3. What was the y? It was 8. 8. Okay. Now comes the interesting part here. Find the algebraic relation between x and y. And that's what we're going to spend time on. Okay. Which is also called eliminating the parameter. We're going to eliminate the t. As I said, you're not too concerned about that. You're just concerned about the time, I should say, the amount coming in and the toys leaving. So I'm not going to start with what they have here. I'm going to start with a simpler example. Okay, so I'm going to have this for you here. So eliminate the parameter in this coming equations. If I said, for example, x is x equals 5t minus 7 and y equals 17t minus 3, 1 second, 17 minus 3t. Okay? And we're asked to eliminate the t's. We do not want to deal with t's. Just give me what's coming in and what's leaving. Okay? So you choose which one is easier for you to work with, either number 1 or number 2. Doesn't really matter, but let's say that I picked number 1. So I'm going to say x equals 5t minus 7. How do you isolate the t by itself? So you're basically solving for t. How do you solve for t? Before I can't really divide by 5 yet, but there's another shell that I have to take care of. Yeah, exactly. I have to take care of the 7 first. So I'm going to add 7 to both sides. So that's going to give me a x plus 7 equals the 5t's. Divide by 5, every single one of them. And that should give you something of this nature. T equals x over 5 plus 7 over 5. Okay. You need now to take the t box. So you made yourself a t box. So I'm going to go here and put, this is my t box. And I'm going to take the t box and plug it in whenever I see a t in my other function. So you're going to take the t and plug it whenever you see the t box, plug it here. Basically, you're doing substitution here. So in this case, these are an arrow here. I'm going to say this is y equals 17 minus 3 times this box here, the t box, which is x over 5 plus 7 over 5. All right, so basically you're going to have y equals 17, then you distribute this guy, right? Negative 3x over 5 minus, what's 7 times 3? 21 over 5. And for the 17, because you want to probably make it just a little bit nicer, These two can combine. Make sure that the 17 is also has a common denominator. So 17 times 5. Can somebody find what is 17 times 5? What is 17 times 5? $85, okay, times 5 over 5 minus 3 minus 21 over 5 minus 3x over 5. All what I'm doing, just arranging these guys. I'm combining these like terms here. And to combine the 17 with 21 over 5, I have to come up with a common denominator. That's why I multiply it by that amount. So now sum is saying it's 85 over 5. 17 times 5 is it 85? Good. Minus 21 over 5. How much is that? Okay. 64. So 64 over 5 minus 3x over 5. Y equals that. I know it's a little bit messy, but remember you have a factory to worry about, so it's not easy to manage a factory, obviously. I'm just arranging things here to make it look a little bit nicer. Okay, so the concept now is this. You have, once you did, I know that we had some fractions here, and we're not fraction freaks, I know that. But once you arrive here, you look closely and you're not going to see any t's here. There's no t's involved. I mean, you started with your x has some t's, your y has some t's, and you eliminated the t's, the perimeter, and you ended up with only a relationship between the x's and y's. There's an x here, see? Y equals negative 3 over 5x plus 64 over 5. So basically, in this case, you just could use a table, you could use a function to graph, whatever that you have to use to get you to the result that you needed. Okay, so let me take this one more time, very slow. Okay, let's see what we did. What did we do in this example? Well, let's take a look. I was given two different equations. Each one of them involved a t, and I was asked to eliminate this t, eliminate the parameter. Okay, I chose an equation. It doesn't matter which one you choose. Sometimes I think I choose the easiest one. It doesn't turn to be the easiest one, but it doesn't matter. So now I have the t equals this box. I'm going to take this and plug it back into the other equation. What happens if you plugged it back in the same equation? Well, guess what? You're going to end up with the same equation that you start with. So it doesn't make any sense. Plug it into the other equation that you did not touch yet. And I did. This has just happened to be a little bit fraction involved. But that's what I did. And then I made a common denominator. And I subtracted. And I end up with the last function here, which is only x's and y's. There's no t's involved. A question here says, can you only remove a t if there are two equations, or can you plug it in into the x function? The two parameters were given. So once again, the one that I have here, there's also, by the way, there's only one parameter. It's a t. But the equation that I have here, I'm giving you this equation. They give you the equation. They give you an equation with x and t and y with t, and they tell you go ahead and eliminate that t. Yep, it's okay. So let's do another one. Hopefully this one doesn't have fractions. Okay, let's do another one without fractions. Okay, I need you to feel good about this once I finish. So another one without fractions. Eliminate the parameter. So let's try this one here. Eliminate the parameter, okay? And this one is going to be, let's say I have f of x, x equals 2 plus t, and y equals 3, say a t minus 3. Okay? This one should be straightforward. That's number one. That's number two. We're asked to eliminate the parameter. Can somebody help me out? What do you think, or maybe choice, or tell me what's the first step? By the way, if you're with me on the live stream, give me something. Say yes. I see some of you are here, actually here. Tell me if you're doing good over there. So I have both. So it says make one of you are suggesting get the t by itself. That is very true. Which one would you like to choose? Number one or number two? One. Okay, somebody's there's kind of a debate between 1 and 2. Let's take 1. Okay, so I'm gonna work with 1. I'm gonna say x equals 2 plus t. If you want to isolate the t by itself, then you gotta subtract 2. So basically t equals x minus 2. I'm gonna call this my t box. I have x box, now I have a t box. Yeah, I had on Microsoft. I'm going to take the t box and then plug it whenever I see a t in my other equation, right? So that's going to be a y equals x minus 2 minus 3. Somebody help me out, please. Y equals what? Exactly. X minus 2 minus 3. Y equals x minus 5. Look at it closely. Does it have any t's? Does it have any parameter? No, it doesn't have any parameter. You eliminated the parameter. There is no involvement of t anymore. It's gone. It's okay. So now let's do the example that they actually have for us here. The example that they have for us is x equals t plus 1 and y equals t squared plus 2 t's. Let me see if actually, yeah, if somebody could provide that link for her, that'd be great. So x equals t minus, is it t plus 1? Let me see. X equals t plus 1. Now the other guy is y equals t squared plus 2 t's. We're asked to eliminate the parameter. So I think that number 1 is easier. I'm not sure about you. So I'm going to work with number 1, and I'm going to say x equals t plus 1. So x, or the t, is going to equal to x. Just subtract the 1 minus 1. So I'm going to take this box here of x minus 1 and plug it into my second equation whenever I see a t, and it happens twice here. See that? So now I'm going to say y equals x minus 1 quantity squared plus 2 times x minus 1. Okay. Let's do some arithmetic here. So t, I know there's a shortcut for this guy here. Which is but you could do the FOIL, you could do FOIL, distribute. The box is probably my favorite, but I also know a shortcut. A shortcut says that you take the first term and square it, and then use this sign here, negative, and then 2 times first times second. 2 times the first term, 2 times x is 2x times 1 is 2x, and then square the second term plus 1. If you are not sure what I'm doing, it's perfectly fine. You could FOIL, distribute, or do the box. You'll end up with this amount here. Plus 2x's minus 1. All what I did right now is just distributed the 2 here. And let's carry on with this. I want to see if there's something that could simplify. Well, it turns out to be that these two can go bye-bye. This one and this one can go bye-bye. And I made a slight mistake. This is actually a 2. 2 times 1 is negative. 2 times negative 1 is negative 2. And all of a sudden you end up with x squared. Then you have plus 1 minus 2. This is simplified to x squared minus 1. Okay, here's your y. And once again, you look at this carefully. There is no t's involved. There is no t's involved here. Okay. Okay. Are we good? Give me a thumbs up if we're good. Awesome. Okay, so basically, again, solving by substitution is what we're doing in this case. The second item, so the first thing that we talked about was the parametric, which is eliminating the parameter. And the second item we're going to talk about is the inverses. And there are 3 types of 3 different ways to find the inverse of the function. 3 different ways to find the inverse of the function. So if you pay close attention, there will be 2 of them are going to be pretty simple. There's one that requires more algebra, so you probably need to pay more attention to that one. There's a graphic one, there's algebra, and there's also algebraic approach. And the third one is actually using the function composition that we have learned before. So 3 different ways. Before we start here, an inverse relation, an inverse function. I want to point out the word relation here. Relation, for example, if you have a graph that looks like this, and I'm going to ask you, do you know if this is a function or not? How do you know if this is a function, if it is a function? And I see multiple are writing at the same time. That's awesome. Exactly, if it passes the vertical line test. So I'm going to go here and then do this and do that and that, vertical line test. Don't forget that. Okay. So now my question is this. If it does not pass that vertical line test, we call it a relation. Okay, so for example, I have this graph here. This graph here, right? This is not a function, right? It's a relation between x's and y's. So keep that in mind. They're telling you here that for a definition of an inverse, if the order pair AB is in a relation if and only if the order pair BA, you finally look at the AB becomes BA, is an inverse relation function. So basically you gotta switch the x's and y's to find out if you have the inverse. Obviously this is kind of the brief description, but not the details. Another way to test is something called the horizontal line test, not the vertical. This is horizontal line test. And this one says the inverse function is a function. I should say the inverse of a relation is a function if and only if each horizontal line intersects the graph of the original only at maximum of one point. What basically they're saying, you have also something called the horizontal line test. An horizontal line test, if you could look through it here, if you're touching whatever graph you have here more than once, then you're gonna know for sure the inverse of what you started with is not a function. So more on this to come, okay? But just basically they're saying there's an idea of a horizontal line test that you could use to help you out find if the inverse is actually a function or not. You have to revert back to the original function and then see if the horizontal line test passes it only one time. If it does, then the inverse is a function. If it doesn't, then the inverse is not a function. Here is another example of this. So here is, look at the furthest, number 1 furthest to the left here. Is this a function? Yes, it is a function. So how about, so I know it's a function, okay? Now let's see if its inverse is a function, okay? So I'm going to use the horizontal line test. I'm going to come here and do my horizontal line test. By the way, you do it everywhere in the function, right? Not just one place. So this is my horizontal line test. So it does pass horizontal line test. Only touch it one time, also one time. So I'm expecting to see an inverse as a function. So the inverse of this guy will be a function of number 1. It's going to be a function. It's not going to be a relation. It's going to be a function. Okay, so more, as I said, more on this to come. The one more definition, it says if f is a 1-to-1 function, then the domain and the range of the inverse function is denoted by f inverse, and that's the notation we're going to use for inverse functions. F inverse. That's -1 at the top here. Doesn't mean 1 over f. It just means f inverse. F inverse is the inverse of the function. And then you see all of a sudden here they're switching the domains and range. So domain, it becomes the range of the other one. The range becomes the domain of the other one. Hence the AB becoming BA. I know all this up until now was kind of a theory thing, but let's take a look actually at some solid ways to find out if you have inverses or not. And one of these solid ways, methods, is for you to use algebra. So method number one is for us to use algebra to determine the inverse, or to find the inverse. So we're going to use that. I'm going to start with an easier example than what the book started with here. And the one I'm starting with here is going to be linear, and the function itself is f of x. Get yourself ready for some notes. I have some steps for you to write down to find the inverse algebraically. So if f of x is equal to x plus 8, okay, x plus 8, step number 1 to find the inverse. Find inverse, which is labeled as such. Step number 1 is to replace f of x with y. So just gonna say y equals this amount. We know that f of x is the y. So y equals x plus 8. What's the first step again? Stay with me. You could use a chat. You could use the live, the streaming on the comment on the stream, or also the whiteboards. Yep. I change f of x to y. Step number 2, you're gonna change every y with x. You're gonna swap the x's and y's. So if I were actually to write down here stuff, I'm gonna actually put it here for you. Change f of x to y. Step number 2, you're gonna swap x's with y's. Every x becomes a y, every y becomes x. So basically what you do here is x equals y plus 8. Easy? Pretty easy, pretty simple. Step number 1, make sure that your f of x becomes y, and then you're going to switch the x's and y's. Step number 3, you're actually going to solve for this y. So solve for your new y. Solve for the y that you just got. And if I come here, I'm going to subtract 8 from both sides. Do you see that? I'm going to subtract 8. I'm going to say x equals y plus 8 minus 8 minus 8. And that should give me y equals x minus 8. And step number 4 is probably the easiest. Change the y, the new y that you got, with f of, basically going to change this with f inverse. So your f inverse becomes this, the new y that you have, x minus 8. Simple as that. So now back to here, your y becomes f inverse of x. So easy 4 steps here. The first one is you change f of x to y. I'm not sure if you want to call it a step, but and then the second one is you change, you're swapping the x's and y's, and then you're gonna solve for y. And once you found this new y of yours, call this is f inverse, the inverse of that function. Well, obviously there are some easy ones like that, straightforward. So there are some cumbersome. Cumbersome, I mean not the steps. The steps are the same. They're just a little bit more involved. For example, if there's some fractions or some square roots or stuff like that. But the steps are exactly the same. They don't change. Steps are going to be the same. So let's take another example before I take the one in the book. I'm going to take... Oh, by the way, what if they did ask you for the domain? So the domain of the f of x here. Does anybody know if there's any limitation for my f of x, the domain here? Is there any limitation here for f of x? I don't see any. That's linear. I could put anything that I wanted for x. Can anybody tell me if you have any restriction for the f inverse, for the inverse function? Do you have any limitations there? No, the answer is no. There is no limitation either here. None of them have limitations. They're doing fine. They're doing okay. Come on. All right. Let's do another one before I get involved in that one in the textbook. And that one is going to be the following. Find f inverse again. Find inverse function of f of x equals, and this one is going to be square root of x minus 3. Okay, I want to find out the inverse of this function algebraically, which is the first method that we are talking about today. Algebraically, I could find the inverse by following 4 steps. Can somebody tell me what's the first step? Change f of x to, oh sure, I'm going to change f of x to y, so that becomes y equals the square root of x minus 3. Second step. What is the second step? Change x's to y's. That's right. I'm going to swap the x's to y's. So I'm going to say this is going to be an x equals square root of y minus 3. And step number 3, what do you think step number 3 is going to be? I'm looking at chat and comments and switching the x and y I did, and then solve for y. That's true. I'm going to solve for y. So to solve for y, I basically have to get rid of the square root. So to get rid of the square root, I square it. So I'm going to square both sides. Basically, I'm going to come here. Let's say square root. I'm going to square the square root. Squaring. Well, this has to be on both sides of the equal sign. And if you do that, you're going to end up with x squared equals y minus 3. So I'm going to pause here for a second because this was a question earlier in the day. I'm going to pause here and show you some things that maybe you know or maybe you don't. I just want to be, I just want to have all of us on the same page. So for example, if you have square root of x, this is exactly the same as x to the 1/2 power. So the square root, because it's got a 2 here as index, it's actually a 1/2 power. Or let's say I have a cubic root of x. So roots are exponents except there are fractions. So x to what power do you think? The third root is x to what power? 1/3, that is true. So obviously the fourth root is 1/4, etc., etc. So what is going on? How did this all of a sudden became like that? Well, let's take a look here on the right side. If you are squaring, so this is x squared, right? If I'm saying 1/2 times 2, how much is 1/2 times 2? That is 1, you're right, because you could just bleep, bleep, that's 1. And that's exactly what's happening here when you square the square root, or when you cube the cubic root. So if you're saying x squared, right, square, you basically are saying x raised to the 1/2 power times that 2, the square. And that's why these two cancel out, and you're leaving yourself with just what's under the square root, with just the x's. Okay? So this is just an insert for those who were not sure why this happened here. Why does the square root cancel the square, or why does the square cancel the square root? It's because the square root is a fraction power of 1/2, and when you multiply that times 2, they will cancel each other, leaving you with 1. Hopefully that helped those who had some questions or in the process of developing some questions. Now I need to solve for y. So I'm going to add 3 to both sides. Y is going to equal to x squared plus 3. What's step number 4? Step number 4. Step number 4. That's very true. So now f of x becomes inverse of x is this amount here. Okay? This is the inverse of x. So as you could tell, I mean, algebraically, it's probably most, I mean, you could see it with your eyes. Some other ones you also get, some other methods you're going to see today. But it's a little bit not just like a graph and a test and stuff. Somehow it feels more confident when you do it correctly, obviously, that you have to inverse the function. However, it's not the only way. It's not the only method. Anyways, before I leave this one, I'm going to go back to the textbook example. It's a little bit laborious, and you probably need to pay more attention to this one here. So this one says, we're giving you a function. And the function itself is f of x equals x divided by x plus 1. A rational function here. Step number 1, if you guys recall, does anybody remember? Step number 1 is what? The y. So I'm going to have a y equals x divided by x plus 1. All right. Then you're going to have to switch. Step number 2, you've got to switch the x's and y's. Okay, so that becomes x equals y over x plus 1. And also we had this question earlier. This is a fraction. X is divided by 1. And then you cross multiply. Bleep. And then bleep. So y times 1, that's a y, equals, hold on a second, am I doing this correctly here? Y times, so I've got x, y plus 1. So x times x plus 1. Hold on one second. I think this one is not right. There's something not right here. Exactly. Thank you. This has to be a y. Thank you. A slight typo here. So I have a y here. It's not an x. Good. So now let's move on. I've got y equals x times y plus x. Okay, y equals that amount. So I'm going to subtract y from both sides. Subtract y, subtract y. This is going to give you a 0 equals xy. I'm basically trying to collect the y's on one side. You could say minus the y and then plus the x. Well, I only needed the y's on one side, so I'm gonna subtract the x from both sides. You doing good? Will we divide by? Yes, eventually we're going to do something like that. So at the current state that we have x minus negative x equals xy minus y. So obviously I want to isolate the y's again. So I'm going to choose y as a common factor. I'm going to factor out the y. So y, open parentheses, x minus 1 equals negative x. Then I'm going to divide by whatever is next to my y, because I only need the y. X minus 1. Once I do that, I see myself looking at, obviously these are going to go away. So you'll be looking at y equals negative x divided by x minus 1. Why did we, okay. So now, there's just some maybe cosmetic or something. They multiplied the top and bottom by negative 1. Which doesn't affect the value of the function because it looks like you're dividing to multiply by 1, right? So and that becomes the new good looking function, which is x at the top, and because you have a negative, so negative becomes, this guy becomes a negative because this guy becomes a positive, 1 minus x at the bottom. And that should be the result, or the step number 4, which is the f inverse of this function is this format here. It's going to be f inverse of x equals x divided by 1 minus x. Okay? This is the inverse of that function. In the x and y is the x and y in the x and y okay, let's see, is it Delaney, are you talking about here at the here where I'm hovering right now with my mouse? Okay, at the top. Above, okay. So how far? This one here? Okay. Delaney, can you tell me how far is this Delaney here? Okay, she's coming back. So x, y plus right here. Okay, so oh. No, this one was for this y. I just moved this y here on the left, not this y here. I can't touch this y. If the y is multiplied by the x, I can't touch it yet. I just moved this y, the one to the left. Yep. I removed that so I can have y's on one side basically. But I cannot subtract that from this. That's why it ended up here by itself. XY did not, I was not able to touch that, and I just subtracted the y from it. Okay, any other question? I know this a little bit because again of some fractions and stuff, but it's the same idea, same concept. You have 4 steps, you follow the 4 steps, and you should be golden. So that was step number, I should say that was method number 1, is to solve algebraically. Method number 2, which is the easiest, by the way. Method number 2 is the easiest. You all know, y'all know that there is a line called y equals x. It's a straight linear line. Obviously, it's a line, so and it's a 45-degree line. This line here. It turns out to be, to find the inverse graphically, you just have to reflect over the y equals x line. You just have to reflect it. So pretend that you are here. Something like that. Okay, you reflect over the y equals x. And if you do see that reflection over the y equals x, then you could claim these two guys are inverses. Let's say number 1 and number 2 are inverses because there is a clear reflection over the y equals x. Okay, so graphically you could tell if they are reflected. So let's see an example that we were given here. I have this cubic line. Apparently this is a cubic function. And the cubic function is shown like this. I have a cubic function here, and if I were to draw the x and y axis, I'm sorry, the y equals x, line, which is here, the 45-degree line, and I'm able to see the reflection, or I could do the reflection myself, then I could confidently claim that these two are inverses. This is actually, this guy is an inverse of the other one. This is f of x. This will be f inverse of x. Okay, inverse of the function. So graphically you could tell again by using the 45-degree y equals x, or the 45-degree line. You basically reflect over the line. So hopefully by now you know how to reflect, right? So even if they don't give you details, you could come here as a perpendicular bisector, right? Let's say that this is maybe 2 units or 1 unit, and you also do the same thing, perpendicular bisector here. This is going back to geometry years. This point has to match this point. You do all this for the others, and you see yourself that you're looking at a reflection over this guy. Excuse my graph, but you got the idea. Okay, so I'm not going to spend more time obviously on this easy part, but we're going to spend time here on the third method. So that was the second method that we just looked at, the y equals x reflection. The third method for inverses is going to be using the composition. And what the composition rule states is this: if the function function f is 1-to-1 with inverse function g, if and only if f of g of x is equal to x and g of f of x equals to x. Basically, you're going to do the inverse, you're going to do the composition from both sides. So f of g of x has to equal x. And also, if you do the opposite composition, f of g of f of x has to equal, there's two parentheses here, has to equal x. And if this happens, then yes, f and g are inverses. And we call this 1-to-1 inverses. Okay? So again, I'm going to start with an easy example. And let's see if that is true. So let's see if these two equations here gonna help me. Start with f of x is equal to, let's say, x plus 3. And g of x is, I'm going to say 3x plus 2. Okay? We need to find out if these two functions are inverses, are one-to-one inverses of each other. Well, there's a way that you could do it using function composition. So let's see f of g of x. If they're equal to 0 to x, you have to equal to x. You're testing, by the way. If it's equal to x, then that's a good sign, and then you move on to the next step, which is the opposite or the other direction of the composition, g of f of x. And it also has to be equal to x. It could be, it could not be. We're not sure. We're testing. So in our case here, I have, which one do you think I'm going to start with? Which function do you think I'm going to start with? Going back to function composition. Function composition. Here we go. Macy, good job. So I'm going to go to put the g function inside the f. So I'm going to say g 3x plus 2. I'm going to put that into the f function, which means I have x, that is 3x plus 2, right? Plus 3, which is 3x plus 2 plus 3. Okay, how much is that? 3x what? Come on, Salma, I see that. That's good. 3x plus 5. And right off the bat, I mean, does this to you look like, does this here look like an x to you? Does this look like an x? Does this here look like an x? No, it doesn't. No, it doesn't. It's not equal to x. It does not equal to x. Then I pause here. I don't have to continue. I don't have to check the other part as well, the other side, which is g of f of x. Well, therefore, I'm just going to pause here. You're going to say therefore or then f and g are not inverses. They're not. I don't have to finish. I don't have to continue that. Okay. Let's see another example. Let's say that I have f of x equals x plus 3. Again, yes, again. And let's say that my g of x is going to be let's say I have negative 3. Okay, I'm being silly, but why not? Let's just try. So if f of g of x equal, we're testing, equal x. So go ahead, Layla, that's fine. If f of g of x equals that, well, I'm not sure. Let's test it. Let's examine that. So I've got here f of negative 3, which means I have negative 3 plus 3. That's a 0. Well, that's not going to be also not a function. You can't even finish. You don't finish. That's not a function. Not a function. Not an inverse function, I should say. These two guys are not inverses, since I did not end up with either equal to that amount. Let's take a closer look at what they have for us in the textbook. So here's an example. It says f of x is x cubed. F of x is x cubed plus 1. And the g of x is actually going to be the cubic root of x minus 1. Let's see if that is if these are inverses. How do you check if these are inverses? Can somebody tell me? How do you check? This is the third method. How do you check if these guys are inverses? That's true. I could use function composition, f of g of x. And I hope that that will be equal to x. Hopefully that is going to happen. So if I put f, I'm going to put the cubic root of x minus 1, cubic root. I'm going to put that into my f function. So cubic root of that means I have a cubic root of x minus 1, cubic root. I'm going to choose a different color for this guy, cubic root. And this is being cubed. What did we say about cubing the cubic root? What does that do? It cancels them out. So you're going to basically end up with x minus 1 plus 1. Okay, well, that's interesting, because now these two are going to go bye-bye, leaving you with x. Well, that's a big happy face here. That's a good start. We're like 50% done, and we're 50% jolly or 50% happy. Let's test the other side now. I want to test, what do you think I'm going to test right now? Exactly, I'm going to do the g of f, the other side of that composition function. So I'm going to say g of f of x. Hopefully that equals to x. I'm not sure. Hopefully, I'm testing. I hope. So now let's take the f of x. What was the f of x, by the way? Does anybody remember what was the f of x? The other side of the mountain. The other side of the mountain. Other side of the mountain. Where composition be. Okay. So I've got x cubed plus 1. I'm going to put that, substitute that into my g function, which is a cubic. What? Cubic root of that. So every x is going to be replaced with x cubed plus 1. And then I have a negative 1 already inside that, which will give me, if you look closely, I'm going to end up with boleep boleep. This boy is going to go. And then leaving you with x cubed. And please do not ignore, this is a cubic root. Okay, so you're basically saying, what's the cubic root of x cubed? Well, definitely that's going to be just the x. Another happy face here. And what we just found out in this example, that f of g, I shouldn't say it like that. Maybe I should use the other notation as well. F of g of x is the same as g of f of x, and actually each one of them is equal to x, equals x. So therefore, or then, or thus, f and g are inverses. Inverses of each other, inverses of one another. They both are inverses. Okay, how are we doing thus far? How are we doing thus far? Good, 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 good. Okay. Hanging in there. Okay. Okay, I'm gonna, I did finish my lesson today, so I'm gonna pause the recording. I'll stop the recording. I'm gonna give you time to do, to start homework in class today. Yay! So give me a second. I'm gonna get started. And outro.